Anyone remembers? The antiderivative of 1 over v. Which function prime is 1 over v? Which one? Plus 3v cubed over 3. This simplifies. I have to plug in 2. And I have natural log. Now I can drop the absolute value. And plus 2 to the third is 8 minus. When I plug in 1, I get 0. When I plug in 1, I get 1. So this is natural log 2 plus 7. Good pick. I want the integral from -1 to 2 from 1 over x squared dx. How do I proceed? What is the antiderivative of this? What function prime is 1 over x squared?
X to the -1.
Very good. You're right. But FTC is not applicable. Why? Why? You are correct. -1 over x prime is indeed 1 over x squared. We have to remember that. This is very important. But why FTC is not applicable here and I cannot write anything?
Has to be continuous.
And where is this function not continuous? And in other words, not defined?
0.
And 0 is in the interval. That's the reason why this cannot be calculated using the fundamental theorem of calculus. This is called, and you will see in the next class, in Calc 2, improper integral, which we do not discuss here. Okay. So we learned a lot about definite integrals. We know that a definite integral is always a number. Definite integrals. The integral from a to b, from f of x dx, of course assuming f of x is continuous, is a number. Now we also have something called indefinite integrals. Section 5.4. And here they are. Or here's an example. No limits of integration. Indefinite. The answer must be a function. Answer is a function. Not just a function. The most general antiderivative, which is a family of functions. So this is f of x plus a constant c. One good thing here is that I can check. I can always check the answer. Which I can never say for this. I can only hope that this is the correct answer. I can go back and do it again or whatever if I have any doubts. But here, for an indefinite integral, I can always check the answer. Always. How will I check the answer? By something I just learned from Fundamental Theorem of Calculus, Part 2. How will I check the answer? By
differentiating.
Exactly. I will differentiate this side, I will differentiate that side. When I differentiate this side, I get the function. When I differentiate the antiderivative, I have to get the function. So let's see how this works, and let's look at examples. I don't like any of these examples here, but we'll choose something. Yes, here's one. The integral from 1 plus tangent squared alpha d alpha. So I'm asking myself, can I determine an antiderivative? Not really, because I can determine the antiderivative of 1, which is alpha. But what do I do with this? I don't know any function whose derivative is tangent squared. But I know an identity that says 1 plus tangent squared equals secant squared. At some point in time, we talked about those three fundamental trig identities. This I like. So I'll change this into secant squared alpha d alpha. And now I know the answer. It must be tangent alpha plus a constant c. Can I check? Yes. When I differentiate this, I get this, which has to be changed into this according to the fundamental trig identity.
So for indefinite integrals, there isn't going to be a lower and an upper bound to it?
That's why they're called indefinite, yeah. And the answer will be a function, not a number. Yes. Let's look at the integral from x squared plus 1 over x squared plus 1 dx. Okay, can I find the antiderivative? Yes. Of x squared is x cubed over 3. Of 1 is x. And you already told me that this is arc tangent x plus arc tangent x plus a constant c. If you have any doubts, when you differentiate the left-hand side, you get this function. When you differentiate this, you have to get the same thing. Bring down 3, get x squared, so differentiate x, and differentiate this into 1 over x squared plus 1. Okay, let's also look at theta minus cosecant theta, cosine, is it, no, cotangent, sorry, cotangent theta, d theta. Can I find the antiderivative for this? Yes. Which function prime is theta? Well, it must be theta squared over 2. Now, is there a function whose derivative is negative cosecant cotangent? And the answer is yes, plus cosecant theta plus a constant c. When I differentiate this, I get theta. When I differentiate cosecant, I get negative cosecant cotangent. When I differentiate c, I get 0. So this is the most general antiderivative, which is basically a family of functions. There are infinitely many functions because c can be anything from negative infinity to infinity. So therefore, we can create infinitely many functions. Okay. I know we have 10 more minutes, so let's choose other problems. I do have a remainder from 5.4, which is basically the total change theorem that we have to talk about, a tiny remainder. And I have to show you the substitution rule, and that will be the end of the material for this class. So let's choose other integrals, anything you'd like. Anyone? Okay, I will choose then, if you don't want to. Okay, I'd like to start with the integral from 1 to 2, from 1 over x squared minus 4 over x cubed dx. We should always have in the back of our minds, is this function continuous on this interval? The answer is yes, because the function will not be continuous or will not exist in this case at 0 only, and 0 is not in the interval. So I highly recommend changing this into x to negative 2 and this into 4x to negative 3 dx. And then the integral from 1 to 2. I didn't need to write that again. Sorry. I can directly find the antiderivative now. I don't need this. So that is x to negative 2 plus 1, which is negative 1 over negative 1, minus 4, x to negative 3 plus 1, which is negative 2 over negative 2, and back this is a definite integral from 1 to 2. I'm going to try and clean it up a little bit before I plug in these numbers, because it's confusing right now. I have negative 1 over x. This would be positive 2 over x squared from 1 to 2. I have negative 4 divided by negative 2, which is 2, and then I bring x to negative 2 to the denominator. And now I plug in 2. Negative 1/2 plus 2 over 4 is plus 1/2. Nice. Okay. Minus, be careful now. When I plug in 1, negative 1 plus 2. So 2 minus 1 is 1, but I have a minus in front, so the answer is negative 1. Here's an interesting one. From negative 1 to 2, from x minus 2, the absolute value of x dx. So on this problem, I have to start by simplifying the function first. We've done this before in limits a long time ago. It seems like a long time ago. So I have to start with the absolute value of x, which has two possibilities. Either x for greater than or equal to 0 or negative x for less than 0. So my next step is this function to simplify. So x minus twice the absolute value of x then has also two options. X minus 2 times x for x greater than or equal to 0, and x minus 2 times negative x for x less than 0. It's not ready yet. So x minus 2x is negative x for x greater than or equal to 0. But this is negative 2 times negative x, which is 2x plus an x is 3x for x less than 0. So therefore, I know that this integral is composed of two integrals. So the interval is negative 1 to 2. But there is a break at 0. So I have negative 1 to 0, and then 0 to 2. Negative 1 to 0 is from 3x, of course dx. And then from 0 to 2 is from negative x, of course dx. Do we understand so far what just happened? Any questions, anyone? Any questions here? Okay, so this is 3. Which function prime is x? Well, it's x squared over 2 from negative 1 to 0. And then minus x squared over 2 from 0 to 2. 3/2 stays outside. When I plug in 0, I get 0, but minus when I plug in 1, and I get 1. Because I took 3/2 out, 0 will be 0. With minus 1 is squared, so it's 1, but I have in the formula for the from the theorem of fundamental theorem of calculus, I have minus. So now here minus, I plug in 2, it's 4 over 2, which is 2, but minus when I plug in 0, it will be 0. So this is negative 3/2 and minus 2. The least common denominator is 2, so minus 7 over 2. Any questions?